Hello, welcome to Formal Lab 1, Spikeball next. Why did we choose Spikeball? Well, Spikeball is a very fun game that involves a lot of energy transfers between the net and the ball. Our question was, how does the stretch of the net for a Spikeball affect the energy of the system after the collision? Our goal was to discover how the inelastic collision of a ball and net changes the system's energy. And our outcome was that as tension increases with the Spikeball net, the change in energy decreases. The inelasticity decreases as you increase the tension of the net through square loop addition. Our method was that we dropped a spike ball from 1 meter onto 4 different varying tightnesses. Tightness 1 represents a tightness of 1 square, and tightness 4 represents a tightness of 4 squares. Our velocity max and peak height before and after will be recorded on each trowel. And then we'll use these to calculate energy, potential, momentum before and after the collision.
Shown here are various tracker depictions of the movement of the spike ball within the 4 different collisions. We started the movement from the exact moment that the ball was dropped to its highest peak after the collision. We calculated both the velocity and the Y movement of the spike ball for each collision.
On the left is the system schema with interactions between the spike ball and the net, the spike ball and the earth, and then a interaction between the net and the earth. In the middle are energy pie chart representations of the ball before the collision, shown as middle left, and then the energy after the collision, with the smaller circles in the middle, and then the little bit larger circles on the right. However, collision represents net energy is lost in the system. And then to the far right is our motion map depicting the general movement of the ball throughout the collision.
Shown here are various results for the collisions for each of the 4 quantitative categories. We found that the lowest change in potential energy for the ball was a stretch of 3 squares at an energy of 0.3272 joules. The highest change in potential energy for the ball was a stretch of 1 square at 0.6156 joules. The greatest change in momentum was again that stretch of 1 square at 0.2107 kilograms meters per second. And the lowest change in momentum was a stretch of 3 squares at 0.0707 kilograms meters per second.
Depicted on the right are energy potential after the collision graph, and then on the bottom is the momentum after the collision graph. You can see that each dot represents either tightness of 1 square, or tightness of 1 square, tightness of 2 square, tightness of 3 square, and all the way to tightness of 4 squares. And then you can see that the energy potential after the collision models a natural log, and the the momentum after the collision models a natural exponent. The linear regression lines were determined by comparing RMSE values and determining the lowest one. Here is a table of all of our measured and calculated values. You can see that we measured the velocity before the collision and the velocity after collision. The velocity before the collision are relatively similar. There really is no pattern or trend to before the collision. However, after the collision, you can see that as the tightness of the net increases all the way to 4 squares, that the energy after the collision, the velocity after the collision is a lot closer to the energy or the velocity before the collision. This represents that there is less loss of internal energy as the tightness increases. The same trend is observed for our potential energy after the collision. You can see that with a tightness of 1, it starts out at 0.015, 0.14, or 0.4144 joules. And the same trend is observed for the momentum after, that as tightness increases, momentum increases.
So in conclusion, tightening the net increases the energy returned to the ball, causing the ball to bounce higher. The change in energy decreased for the first 3 quantitative increases in net tension, and the loss of energy to internal energy from the stretching of the net decreases as the net behaves more like a solid wall. An improvement to our study would be to determine the linear regression curve using more trials in order to best draw conclusions from the experiment.